Internal defects. This is a fun lecture. Did you just whisper? Prove it under your breath? How audacious. I'm just kidding. This is a fun one though. So internal defects will be the topic of today's little lesson. In the textbook, it is page 222 to 227. And what we're talking about here with internal defects are how there are imperfections in the regular, repetitive, periodic order. And these internal defects are actually the norm. It's a very common thing to have within all different types of minerals. So we're going to say that imperfections to the internal order, imperfections to the internal order are the norm. Every mineral everywhere has these. It just can't, nothing can be truly perfect. The effects of internal defects are actually quite significant. We're going to say the effects first and then get into the different processes. But the effects are very diverse. You will get changes produced to color and strength. That's probably the two most important ones. Color and strength of a mineral can be changed depending on how many imperfections there are, right? The imperfections will stain, you can kind of think of that way, the mineral, and most of the time they'll weaken the mineral as well. You can also change things like growth rate, nucleation rates, conductivity, all sorts of different things can be changed by these imperfections. We're going to use diamond as our example for everything throughout this lecture, which is why, in my opinion, it is a fairly fun one to talk about. Of course, we all know diamonds because of this little lady and logo right here, right? De Beers in the 1940s coined this slogan, "A diamond is forever." A marketing genius of a slogan. And now 75% of all engagement rings in America are diamond engagement rings. This has massively been manipulated by the diamond industry, but this is not a business class and we will let it be. Actually, although I wanted to say this, they've had many other slogans that besides diamond is forever. One has been 2 months salary to try to tell you what price you should pay. Here's another good one. She had her own mind and got me one. Trying to make men wear diamond engagement rings. That one also didn't go over well. Okay, anyways, let's move on. We're scientists here anyways, even though there are interesting anecdotes that abound on this topic. The types of crystal defects that are present, there's 4 of them, and to show the types, we're going to draw our own lattice. Choose 2 dimensions. We're going to draw a carbon lattice, equally spaced little carbon, and we're going to have them slightly offset in the next row. So go ahead and start making this pattern on your page, please. 3rd row is exactly like the top row. Maybe do like 5 layers of this. And we're going to use the misplacement. None of these have been misplaced yet. So like if you're using pen, I'm going to erase one of these and I'm going to erase another one of these and I'm going to draw on this to show how we can take this perfect lattice, which you and I are drawing right now, and how we can change it chemically or with strain and deformation to change the mineral. So the types, we're just going to label them right now. We're going to have a type of defect that's called like a missing lattice point, and that's just a vacancy in the lattice. So for our example, let's do this. We know there's a point right here. However, with the friendly eraser, I can get rid of it. So that is one example, and I'm going to go like this, dot, 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 dot. It should be there, question mark, where'd it go? Well, it's now missing. There can be a type that's called a misplacement. And this is where one of them just kind of gets moved from where it should be to somewhere else. So let's say it moves like that, and it is now here messing up the lattice and no longer there. Okay, that's a type. Then we'll need another color. Let's go with green. This is called replaced. These should all be carbon, yeah? But let's say that a boron or a nitrogen sneaks in and fills that lattice spot, and it doesn't have the same charge, right? Ionic charge. Maybe it is like, what's carbon? Carbon's +4, right? Well, what if nitrogen's only +3? Well, that's going to change the not only the atomic lattice, it'll change the electron configuration in that area as well. So this, let's just say that this is a nitrogen that is substituted in to the carbon lattice. That happens all the time. And then the last type of is called a linear defect. We can sometimes call those dislocations. And so it would be like some kind of offset is occurring along a linear feature throughout the lattice. Okay, so those are our types. And now let's just walk through each of them with our notes. And I'm going to show you pictures of diamonds that demonstrate colors in particular that are produced from each one. And that's one of the really cool things about diamonds and defects, is that all the different colors of diamonds are, what am I doing here? I'm getting distracted because I'm talking about diamonds. Point defects. This is going to encompass the ones that are missing, the ones that are misplaced, and the ones that are replaced. And then later we're going to get to line defects, which will be big B. So our different types of point defects, we already mentioned this. The missing points in the lattice, this is going to create a vacancy in the lattice. The vacancy in the lattice also tends to change the way light interacts with the crystal structure, tends to change light interaction. It doesn't really change the chemistry, because you're just like, there's a C, and now there's no longer like 1 C, well, 1 part per million or something. That's not going to do too much, but it could change the electronic environment, and therefore it could change how color works. And oh boy, that's a big picture. We better shrink that down. These pictures are coming from different diamond textbooks, and also from Smithsonian's pictures, and also from GIA, Gemological Institute of America's picture book. So we are going to put, like, let's just say an example, brown diamonds. These were used to be worthless until they came up with this phrase like, chocolate diamond, get her a cognac diamond, right, to take away the ugly color, brown. And that has increased sales massively. Now, they're beautiful diamonds in their own right, but it's true, brown's not necessarily the color that goes with everything, more like fall colors. But here I am not talking about science again. Let's get back to it. What ends up happening is that you get these deformation that occurs. Deformation in the lattice of the diamond will actually remove big clusters of carbon, just moves them out of the way. And like you'll get like pockets of like 60 carbon atoms that should be there that are no longer there. And that vacancy absorbs light, making the diamond brown. So deformation in lattice removes clusters of carbon, right, giving you the brown color, hence that picture. Now, let's do another example. I made this a little messy. Green. A green diamond costs about $1 million a carat. A white diamond, a clear one like we tend to see, those are worth around $5,000 a carat. Now, the reason is because they're exceptionally rare and they are stunningly beautiful. So here's a beautiful example of a green diamond. I think this one in particular, something like $10 million. Incredible stone, beautiful rich green color, all the sparkle you normally would get in a diamond. And what happens with green diamond is that radiation, so here's our lattice, okay, and you'll get radiation coming from, let's say, a zircon crystal or something like that, that hits that atom and knocks it out, creating for us sitting here a vacancy. And it's that vacancy that will absorb green light, or absorb all the light besides green, giving the diamond green. So let's just say here that radiation knocks carbon loose. Why did I say zircon? Well, zircon has uranium in its crystal lattice, and the uranium will release radiation that could penetrate into a diamond. Anyways, maybe we're getting too deep for a topic. Let's move on. Number 2, a misplacement in the lattice. Well, this is just where a carbon would be in the wrong position. It doesn't change the composition. It really doesn't change the electronic environment, and therefore it doesn't affect light. So there's no diamond example to put here. So we're just going to write down here that atom is in the wrong position. Atom is in the wrong position. Composition is not affected. Almost nothing is affected. Composition is not affected, at least like, in diamonds. And those are the examples we're doing today. The third type, this one has some really cool diamonds. This is replacement. And we're replacing what should be there with some foreign ion. So replacement, this is a, we'll say this, replacement by a foreign ion. It tends to be at like the ppm, right? That stands for parts per million, or ppb, parts per billion level. So what does this mean? These are really low concentrations. And the biggest effect that something at that low concentration will have will be on color. You'd need a lot more of it to affect things like strength. Well, I already mentioned yellows. And so nitrogen is an exceptionally common element in our atmosphere. And so there's many, many opportunities to stain a mineral with the incorporation of nitrogen. And this happens in diamond, where a cluster, you can get single nitrogens, but a lot of times you get these clusters of like 3 nitrogens that end up entering into the carbon lattice, the carbon diamond lattice. And it will, there's like a little vacancy in here and ends up absorbing light. And so we're going to say here that this gives the color yellow to diamond when nitrogen occurs inside of it. And this is so common, in fact, that you know how there's the 4 C's? Oh boy, what happened? There we go. There's the 4 C's of diamond buying. Maybe you've never heard of this. It's cut, clarity, carat, and color. Well, the number one thing you're worrying about with color is how yellow a stone is because of how much nitrogen is inside of it. Here's just an example of a yellow diamond from Arkansas, a place where you can go and actually mine. It's the only place in the world where you can mine diamonds from the primary kimberlite in the world. I take my students there. I look forward to doing it again this year. Okay, so a little background there. Now, the most famous diamond in America is colored by the replacement mechanism, and it is called the Hope diamond. And the Hope diamond forms from the replacement of boron into the lattice. Essentially at the ppb level, very, very low amounts of boron. But if you can get a little boron in the crystal lattice, you can take diamond and color it blue. So this is the Hope diamond. It's hosted in the Smithsonian Institute. It's 45 carats, so about as big maybe as a small chicken's egg, and it has a value of about $250 million. But really it's actually kind of priceless because it's such a rare stone. Now, the final type of defect that we can have in a stone, in a diamond, or in other crystals, they're called line defects. We already drew it on our sketch up top. Line defects are commonly called dislocations as well. Dislocations. Because you'll create this offset in the crystal lattice. And let's just say that. Let's say there's a linear offset in lattice. Twinning is another thing that can do this, like we talked about before. Now, our example, actually I scrolled down too far. Our example for the diamonds to show them is pink diamonds. Pink diamonds occur because of carbon. So here's our lattice. Carbons all lined in a perfect way. And deformation occurs in the Earth's mantle where the pink diamond is, and you will get a linear defect, and the carbons will just kind of be offset slightly across that. That offset changes the way light's absorbed, and it creates a pink color. Okay, so here we have deformation in mantle deforms carbon lattice. So there's nothing added to a pink diamond. There's no boron or nitrogen. It's just pure carbon, but the carbon's been offset within itself. Here's an example of a pink diamond, raw, that hasn't been faceted, a stunning and strong color. A pink diamond's worth maybe $400,000 to $600,000 a carat. So many, many times more valuable and rare than a white diamond. It's the rich people of the world, the celebrities that get to buy these, right? So here's a good example of a pink diamond that's been faceted, a stunning color. Now, and then just one last thing I want to say, just as a note, is that you can have, we're going to put it in, we're going to say there can be planar defects. And that's kind of when you have like a line connecting to a line, connecting to a line. Well, it ends up creating a whole plane that now is a defect. So it's kind of like a combination of multiple lines. Multiple lines. And that, dear students, is how crystals deform. And that's really your take-home, I would say, image to think about and study.